In this video, I'm going to show you how to train and deploy a TensorFlow model on AWS SageMaker using SageMaker Notebook. This tutorial is intended for those who understand the basics of training machine learning models, particularly neural networks, and want to learn how to train and deploy such models on AWS SageMaker. If that sounds like you, then let's get started. Here are the steps we will follow to train and deploy a SageMaker model endpoint on AWS. First, we will create a SageMaker Notebook instance. In this tutorial, I will use a SageMaker Notebook instance to write the code. While AWS SageMaker Studio is an option, I have chosen the Notebook instance for its cost effectiveness. Second, we will prepare a data handling script. The script will clean, preprocess, and upload the training and validation datasets to an S3 bucket. Third, we will create a training script. This script will be used for training the TensorFlow model using SageMaker. The goal of this script is to build a model capable of classifying a satellite or Earth data into one of these classes: sea lake, forest, highway, residential, river, industrial, hibiscus vegetation, grassland, or annual crop, as depicted in this image. In the fourth step, we will create the inference script. The goal of the script is to fetch the deployed model, which would be typically residing in the inference container, and serve it to the clients making requests. While the inference code can be integrated into the training script generated in step 3, I have chosen to keep them separate for this demo. This separation makes it easier to extend the inference capabilities in the future if needed. Final and the fifth step is that we will write, train, and deploy job notebook. This notebook will be used to orchestrate the training and the deployment of the TensorFlow model using the SageMaker API. This notebook will reference both the training and the inference script created in step 3 and 4 respectively. Now, let's jump right into step 1, creating a SageMaker notebook. Click on Create Notebook Instance. Enter a name for your notebook instance. For example, you can use AWS SageMaker tutorial. For notebook instance type, select ml.t3.medium. This instance type is under the SageMaker free tier and provides 2 virtual CPUs and 4 GB of memory, which is sufficient for our needs. Under platform identifier, choose Amazon Linux 2. For the IAM role, create a new role. This role will grant the notebook instance access to AWS services such as S3 bucket and SageMaker. Finally, click on Create Notebook Instance to start creating the instance. But note that it may take a few minutes for the notebook to be ready, so please be patient. When the notebook instance is fully created, start the notebook. Now, let's move to step 2, creating the data handling script. We need to create a data handling script called dataprocessing.py to clean, process, and store our satellite training and validation dataset on S3 bucket. This is the typical workflow when working with datasets on SageMaker, although data stored locally on our notebook instance can also be used. Before writing the script, let's upload our dataset called headdata.h5 into this notebook's instance environment. Next, we will define a function to load the dataset into our environment. So here is the code to do that. When you run this script, it shows that the training dataset contains 19,200 RGB images, that's red, green, blue images, which means it's a colored image. And the testing dataset contains 48,000 RGB images. When we visualize the dataset, we see the images are displayed as expected. This also confirms that the dataset is loaded correctly. Because I would like the training to be faster, I decided to select a subset of our entire dataset to be used for the training and testing. I accomplished that using this code. From the above code, the fraction equals 0.3 will select only 30% of the entire dataset that I have loaded earlier. I have divided the selected subset by 255 so as to have the dataset normalized. Now we need to convert the selected subset to Pointe file format for faster storage and loading from S3. Before doing that, we will create a data folder to store the Pointe file locally. Here is the code that converts our dataset to Pointe file format. The dataset is first converted to a data frame as shown here, because Pointe is a columnar storage format designed for structured data, typically represented in a tabular form. Once that is done, we then convert it to Pointe as shown here. Check the data folder to confirm the files are stored there. Finally, we upload the dataset from the data folder to the S3 bucket using Boto3 package as shown here. The dataset will be stored in a bucket named model data 1, 2, 3, 4, 5, 6, 7. The S3 part where this dataset will be stored is represented here. Now let's check the S3 bucket to verify that the dataset has been uploaded successfully. And as you can see, the data is presently on this S3 bucket. And when you click here, you can see the model URI of this data that we just uploaded. If you are following along, please ensure that the S3 bucket where you are saving the train and test data is in the same region as your notebook instance. Otherwise, you may encounter errors when reading your dataset from S3 bucket during training. So for example, if your notebook instance is hosted in US East 1 region, make sure that the S3 bucket where you are uploading your dataset is the same as US East 1 region. Now, let's move on to step 3, creating the training script. As mentioned earlier, this script, which we will call train.py, is where our training code will reside. The primary goal of this script is to build a model that can predict the class of a given satellite image. And according to the provided dataset, there are 9 possible classes a given satellite image can belong to. Let's start populating this training script with relevant codes. First, we need to import the necessary libraries. Here is the code for that. In this script, we will be using TensorFlow framework to build the model, with Keras serving as a high-level API within TensorFlow. We will utilize the VGG16 pre-trained model as our base model. ArgParse is a model in the Python library used to create user-friendly command line interfaces. It allows you to define the arguments your program requires, handle the parsing of those arguments, and provide help and error messages to users. The next step after importing the libraries we need is to load the dataset. So we will write the code to load the dataset, and here is the code. In SageMaker, there are predefined environment variables that can be used to identify variables within an environment during runtime. SM, which I believe stands for SageMaker_channel, is one of those variables used to identify the data being used for training. Keep in mind that while SM_channel is constant, you need to append a suffix to uniquely identify the specific dataset you are using. In this part of the code, we will use the environment variable SM_channel_trainx to identify our training data file trainx.parquet in the training environment. Similarly, we will use SM_channel.trainy to identify the training data labels. The same process applies to the test data. In this code section, we convert our Parquet dataset to NumPy arrays, which is the expected data format for the VGG16 pre-trained model we are using. Here is an explanation of the reshaping process. The trainx_dataset and testx_dataset data frames are converted to NumPy arrays and reshaped into a 4D array where the first dimension, represented by -1, is automatically calculated to accommodate all the images. Typically, this -1 is like a value that represents the length of all the data sets used. For example, in the trainx_dataset, assuming it's 100 images that are stored in this dataset, then the -1 typically represents 100 images. The second and third dimension, represented by 64 respectively, represents the height and the weight of each image. The fourth dimension, represented by 3, represents the color channels, that's red, green, and blue. For example, if trainx_dataset contains 10,000 images, each image being 64 by 64 pixel with 3 color channels, the resulting shape will be 10,000, 64, 64, 3, which represents the 4 dimensions. Next, we now need to write the main code that will train the model, and here is the code to do that. So first, we load in our data set using load underscore dataset function we have already defined earlier. Next, we convert our dataset labels to one-hot encoding, since that is the format required by the TensorFlow framework. Next, we will load our VGG16 pre-trained model. So while the detailed explanation of the VGG16 architecture is outside the scope of this tutorial, I will highlight important points relevant to the code we have written here. The VGG16 model pre-trained on ImageNet consists of 13 convolutional layers, 5 max pooling layers, and followed by 3 fully connected layers for classification. These fully connected layers, often referred to as the top layers, are responsible for taking the features extracted by the convolutional layers and making predictions. So by setting include underscore top to false, we exclude the last 3 fully connected layers. This is because we want to add our own custom layers tailored to the task of classifying different satellite images. The flattened layer converts the 3D feature map into a 1D vector, which can be processed by the fully connected layers we added. We added these 2 fully connected layers because we want to train them to classify our new data, that is the satellite images, more accurately than the original ImageNet data the model was trained on. The first fully connected layer has 256 units or neurons, while the second fully connected layer, which is like our output layer, has 9 units or neurons corresponding to the 9 classes for classification. Here we use the softmax activation function in the output layer because it is a multi-class classification problem, and softmax is ideal for this kind of problem. This line of code prepares the model for training. For the optimizer, we are using Adam Optimizer. For the loss, we are using categorical cross entropy, which is ideal for multi-class classification. Metrics defines the metric to be used to monitor the model during training, and here we are choosing accuracy as the metric to be used. This line of code fits the compiled model on the training data. Train X and train Y underscore one hot are the training data and labels respectively. Epochs refer to the number of complete passes through the entire dataset during the training process. Batch size determines the number of samples used in each training iterations within an epoch. Validation data serves as optional validation data. During training, the model is evaluated on this data after each epoch. Test X and test Y underscore one hot are used here as the validation data and label respectively. This line evaluates the trained model on the test data to access its performance in terms of accuracy, as indicated here. Here, we save our model in the environment using the sm underscore model underscore there variable represented as args.model underscore here. This is a SageMaker predefined environment variable that references the path to a saved model in the training container, which is opt/ml/model path. Finally, we create an entry point for running the above script using this code. Argparse.argumentParser creates an argument parser object which will handle passing command line arguments in Python. Parser.add_arguments adds various command line arguments that the script can accept during execution. Here we've added some of those arguments that should be accepted. The first one is epoch. Epochs will specify the number of epochs for model training, and our default here is 10. The learning rate, will specify the learning rate, and the default here is 0.0001. The other one is per device train batch size, which specifies the batch size for the training data, and the default is 10. Per device eval batch size defines the batch size of the evaluation data, and the default is 10. The model there references the model directory where the model will be saved after training. Depending on the model you are training and what you are hoping to accomplish, the parameters and hyperparameters you specify using the parser.add_argument may differ. Now that we have written our training script, let's create a train and deploy job notebook. This notebook will execute the training and deployment process, referencing the train.py file we just created and the inference.py file that we will create later. So first we import the necessary libraries. Then we specify the dataset URI. The dataset URI is the path to the S3 bucket where the datasets are stored. You can obtain this value by clicking on the file in the S3 bucket. And next we specify the SageMaker session and role. The session is used to manage interactions with Amazon SageMaker and other services, while the role ensures that the training job has the right permission to interact with AWS services. Note that this role is the same as the role we generated when we created this notebook instance. Next, we specify hyperparameters values. These values will override the default values specified in the train.py file using argparse.add_argument. Next, we will specify the parameters that the SageMaker TensorFlow framework will use. Here is the code to specify the parameters. So let's go over what these parameters mean. py_version specifies the Python version you want the framework to use. Entry point specifies the training script you want to use. In our case, it is the train.py file. Framework_version references the version of the TensorFlow we are using. Hyperparameters references the hyperparameter we created earlier. Instance type specifies the type of EC2 instance you want to use for the training. Instance count specifies the number of instances you want to use for training. Role is the same as the role we specified earlier. Here, the debugger hook config is set to false, and disable profile is set to true so as to reduce the overhead during training, um, you know, thereby keeping cost low. When we have specified all the parameters needed, then we call the estimator.fit as shown in this code here. The data channels or the dataset URIs is the dataset that will be utilized by the TensorFlow framework to train the model. When this code is executed, it starts running the train.py file. Before going ahead to run this code, let's go over what the execution of train.py file will look like. The variables created using parser.addArgument are set to their default values, and then the train function is called. When the train function is called, it loads the dataset through the environment data channels: SM channel train X, SM channel train Y, SM channel test X, and SM channel test Y. The dataset is pulled from S3 bucket and saved to these channels when estimator.fit is executed. After the dataset is loaded and processed, the VGG16 pre-trained model is downloaded, training takes place, and the resulting model is stored. Now, notice how args.epochs, per device train batch size, is used to reference those environment variables. Note that the hyperparameters specified in the train and deploy job notebook override the default values set in the train.py file. For example, the number of epochs will be set to 1 as specified by the hyperparameter instead of 10 specified in the train.py file. Now let's run the estimator.fit code. We will wait for the model to complete training, and once the training is over, we will resume. Okay, so I had to restart the training all over again because initially I was using Conda TensorFlow 2 Python 10 kernel, and it failed. Also, here I didn't, instead of the if statement to be at the end here, and everything here was not properly aligned. The if was supposed to be at the end, and then a tab separate to keep this, based on the Python rules. So I had to make this change, and changing the kernel here to be just Python 3 instead of Python 10, because my Python version is actually less than Python 10. It's Python 3.9. So because of that, the initial one I started failed, so I'm kind of restarting a new one, and we'll be back when the training is complete. The model training is complete, and you can see the training was successful. The model has been uploaded to the S3 bucket, and under the SageMaker training environment called SM training env, you can see that the number of epochs used is 1, confirming that our hyperparameters indeed overrode the default values specified in the train.py file. Now that the model has been trained and uploaded to the S3 bucket, it is time to write our inference script. We will call this inference script inference.py file. Here is the code for our inference. The model_fn function in this script reads from the model directory of the inference container, usually opt/ml/model, to load the model for serving predictions. An interesting question that needs an answer is, How does the model move from S3 bucket, where it was uploaded after training, to the opt/ml/model directory in the inference container? Now, this is made possible with the following code. Because we are still using the estimator used for training, SageMaker automatically knows about the last model that was trained. When we deploy the model using this code, SageMaker copies the last successfully trained model from S3 and moves it to the opt/ml/model directory of the inference container for serving. This setup deploys a real-time inference endpoint. However, if you want to deploy a specific model that you have uploaded to the S3 bucket previously, you would use a different approach, because this estimator approach only has access to the most recently trained model, which is the model that was trained using estimator.feed shown earlier. Now let's run this code. The deployment takes some time, so we are going to wait until the deployment is complete and we will resume back. The deployment is complete. But before we move ahead, let me highlight some important points. So I changed the inference from inference.py to inference_script.py and also change it here, because when I ran the estimator.create model the first time, it failed because the inference container for some reasons did not have pandas installed on that environment. The fact that my code, the deployed model does not necessarily need pandas for it to make the inference, for the inference container to make the inference. It just makes sense to comment it out or remove it, which is exactly what I did here. So that's just a way to work around it. I had to change the name because sometimes when you don't change the name, the inference container still thinks it's the same script, so it doesn't change anything. So because of that, I changed the name from inference to inference_script and also referenced it here. And when I made these changes, the deployment worked and it was successful, as you can see by this symbol. And another thing that that is worth pointing out is you can check the endpoints. When you check the endpoints, you will see this endpoint that is now in service. And when you click on it, like when I was having issues, what I actually did was just to click on this link here, and which shows you the logs. So when I was looking at the logs, which is here, it was this logs that helped me figure out where the problem was, and then I changed it and then it worked. So whenever you are having issues, come to the endpoints, find the one that you are training, to usually say in service or creating. Just click on it, and then when you click on it like I just did, it links you, it shows you the logs, and then you click on this and then it will lead you to the logs and you can fix whatever the problem is. Alright, so our deployment is successful and is working. Now let's test if we can hit the deployed endpoint. First, we load our test data along with its labels. The test data is used to test our deployed endpoint, and the labels help us evaluate how accurately our model classifies the satellite data. We are loading it from our local file path in the data directory. You can also load it from S3 bucket if you want to. Next, we will write a simple function to visualize the data we are passing to the deployed model, as shown in the code here. Finally, we will write a code snippet that sends the input test data to the deployed model using the predictor.predict method. Here is the code. These two lines of code preprocesses the input data into a shape that can be accepted by the deployed model. If the data is not in the correct format, the deployed model won't be able to process it. Now let's run the code. As shown, the predicted image shows the predicted class and the actual class it belongs to. This shows that the deployed model is working because when I passed the input test data into the predictor.predict method, it actually produced a predicted images like we've just seen. So with this, we come to the end of this demo. I will go ahead and do a cleanup by deleting the endpoint I just created. I'll do that using this code. Please delete yours as well to avoid attracting further charges. In this tutorial, I demonstrated how to train and deploy a TensorFlow model using SageMaker. We discussed the 5 key steps to achieve this. First, you create a notebook instance to set up your SageMaker notebook environment. Second, you create data processing.py file, which you process and store your data in an S3 bucket. Of course, this is an optional step and you can definitely use datasets stored in your notebook instance to train the model. Third, create the train.py file that will be used for training the model. Fourth, we create the inference.py file, and this script will be referenced during deployment of the trained model and will instruct the inference container on where to fetch the model for inference. And finally, we'll create the train and deploy job notebook. This notebook is used to orchestrate training and deployment of the model. So, I hope you found this tutorial helpful. Thank you for watching and I look forward to seeing you in the next one. Don't forget to like and subscribe to this channel for more insightful tutorials like this.